Okay, let's dive right into this. We're about to explore a really strange but fascinating corner of logic. It's a whole field that's dedicated to a very specific and, honestly, a very weird problem. How in the world do you talk logically about things that just don't exist?
So, let me start by asking you a question. It's a classic. Is the present King of France bald? Just think about that for a second. Is the answer yes? Is it no? Or is it something else entirely? If you're finding it hard to land on an answer, you're in good company. Because in the world of formal logic, this question is actually a beautiful little trap. It's a statement about something that doesn't exist, and, well, traditional logic systems, these just completely fall apart when they try to handle it.
So, to untangle all this, here's our game plan. First, we're going to dig into why this non-existent king is such a big problem. Then we'll look at a special kind of logic designed to fix it. We'll check out how two philosophical heavyweights, Frege and Russell, tried to solve the issue. After that, we'll touch on how we make sure these new systems are actually reliable. And finally, we'll see why any of this actually matters in the real world.
All right, first up, let's get to the very heart of the problem with this imaginary monarch. Why does he cause so much chaos for these very formal, very precise logical systems?
So here's the thing, the core of the issue. Classical logic is built on this really fundamental assumption. It just assumes that every single name or term you use actually points to something real out there in the world. So when you say the moon, it points to, that big rock in the sky. But when you say the present King of France, well, that name doesn't point to anything. It's an empty name. And that's the exact point where the whole system just crashes.
So, to solve this, logicians needed a totally new tool, a system that didn't have to make that core assumption. And this is what led to a whole new kind of logic, a logic that is, so to speak, free from the burden of having to exist.
And this is it. It's called free logic, and its definition is actually pretty simple. Free logic is basically a system that just says, hey, it's totally okay if some of your names are empty. We can still work with them. It's designed from the ground up for exactly these situations, where terms might, as logicians say, fail to denote. Now, the specific kind of phrase we're really zooming in on here is called a definite description. It's pretty much any phrase that starts with the and is meant to single out one and only one unique thing. The present King of France, the tallest person in this room, the person who wrote the script. These are the phrases that are at the very center of our puzzle. So how do we actually handle these definite descriptions when they don't point to anything? Well, this very question sparked a legendary debate between two of logic's greatest minds, Gottlob Frege and Bertrand Russell, and each of them came up with a really brilliant but totally different solution. This table does a great job of laying out their two approaches. So on one side, you've got Frege. He was kind of a traditionalist. He wanted all terms to point to something. His clever solution? He basically invented a special null object, like a designated placeholder for all empty terms to point to. And since that null object isn't bald, the statement the King of France is bald becomes false. Simple enough? But then you have Russell, who took a way more radical path. For him, the King of France isn't a name at all. He said it's a kind of hidden description that, when you rewrite it to show its true logical form, also makes the whole statement false. And what's really fascinating here is that the underlying system you use really matters. If you take one of these theories and you plug it into different flavors of free logic, and there are a few, you can actually get different results. So it's not a one-size-fits-all kind of solution. Now, when you invent brand new logical systems like these, you have to prove they're actually reliable, right? You have to show that they don't have some hidden flaw or contradiction just waiting to pop up. So how do logicians do that? Well, they turn to a field called proof theory. The main tool for this job is something called sequent calculus. I think the best way to think about it is like an engineer schematic, but for logical proofs. It allows logicians to map out the entire structure of an argument, step by step, and analyze its properties to make absolutely sure everything is sound. So a huge achievement in this field is proving something called the cut-elimination theorem. Imagine a proof is like a route on a map. A really complex proof might have all these weird detours and side streets. Cut elimination is a procedure that systematically removes every single one of those unnecessary steps. And what you're left with is the most direct, efficient, and clean path from your starting point to your conclusion.
Proving this for a system is a really big deal. It shows that the system is well-behaved and totally robust. Okay, so I know we've been pretty deep in the weeds of logic and philosophy, but what's the actual payoff? Why does sorting out the King of France really matter here in the 21st century?
This is where it gets so cool. The philosophical problem of empty names has a direct one-to-one parallel in computer science. What do you do when a function in your code doesn't have a valid output for a certain input? I mean, think about dividing by zero. That's what programmers call partial functions, and it is the exact same problem as our non-existent king, just dressed up in a different context. And the solutions that were developed in free logic are now absolutely essential tools in these fields. They help programmers manage errors and create much more reliable software. They're used in something called constructive mathematics, where you can't just assume an object exists, you actually have to build it. And of course, they help create stronger, more rigorous formal systems for all kinds of complex theories. So the big takeaway, the thing to remember, is this. What started as a purely philosophical puzzle about a bald king has actually given us the logical machinery to build more robust, more reliable, and more intelligent systems out here in the real world. It's a perfect example of how really abstract thought can have incredibly practical consequences. And that brings us to our final thought. I want to leave you with this question to ponder. If we can spend all this time and energy creating such elegant, powerful, and useful logical systems for things that aren't even real, what does that tell us about the complexity and maybe even the beauty of the logic that governs the things that actually do exist?